Okay, in this video I'm going to look at problem 85 from chapter 25. 85. So this problem is about the Tevatron accelerator at Fermilab, Illinois. It's designed to carry an 11 milliampere beam of protons traveling at very nearly the speed of light, which is 3 times 10 to the 8 meters per second, around a ring 3,600 meters in circumference. How many protons are in the beam? Okay. So we have a beam of protons that go around in a ring. Okay. So this is probably very, very thin with respect to its radius. This ring has a radius of 3,600 meters, or 6.3 times 10 to 3 meters. And there's a, let's say that they are going in this direction. It carries a current of protons. So this current, or the charge per unit time, is 11 milliamperes. So 11 times 10 to minus 3 coulombs per second. And the speed at which these protons move is nearly the speed of light, which is 3 times 10 to the 8 meters per second. Okay? So this is all that is given. They're asking for the total charge. They're asking for the total number of protons that is actually moving in the ring. So the number of protons is what's being asked. Okay. So how do we approach this problem? Now we have these protons, which are supposedly uniformly distributed around this ring, and they're moving at a constant speed. These are, of course, simplifications, but by and large, they actually hold to a very good degree of approximation. They have to be like uniformly distributed, otherwise this current would not be constant. If they were like concentrated, if there were like humps, then as the humps pass through, then you would have an increase in current, and when the depleted parts pass through, you would have a decrease in current. But this could also be the average current. It doesn't actually change our argument. So these protons that are distributed over this ring, they just go around at a crazy speed, near the speed of light, and this corresponds to some current. Okay? So this corresponds to 11 times 10 to minus 3 coulombs passing through a given point. That's what current is about. So let's choose this point, let's say on this ring, and over this ring, every second, 11 times 10 to minus 3 coulombs of charge passes through. Okay? And this is due to the protons. The charge that's in the ring is provided by the protons. So how fast do they actually go around this? Okay? So one thing we can easily calculate is the period of rotation for these protons. And then by finding the period of rotation, we can estimate the number of protons inside the ring. Okay? So first let's find the period. So this period is going to be the circumference. Oh, this is not the radius, this is the circumference. So it's going to be the total distance traveled divided by the velocity. Okay? So the circumference length divided by velocity is going to be the period that it takes for these protons to go around, and this is 6.3 times 10 to minus 3 divided by 3 times 10 to the 8. This comes to 2.1 times 10 to minus 11 seconds. Okay, so this is very, very, very short. So I was saying that during 1 second, 11 times 10 to minus 3 coulombs of charge passes through, but in 1 second, many periods are completed. So how many periods are there in 1 second? Okay, so what's the frequency? That's of course just 1 over this number. And that will correspond to a very large number. So in 1 second, you're going to get a lot of revolutions of these protons. Now, if you calculate how many revolutions of these protons are there, then you can divide this number. So in 1 second, there are a certain number of revolutions, and in 1 second, this much coulombs of charge passes through. You can find that how much charge corresponds to a single revolution. Okay? So from this period, you can find how many revolutions take place in 1 second. From this, you can find how much charge passes through 1 second. You get their ratio, and you get how much charge there is in one revolution. Yeah, so this is one way to go about this. Another way to go about this is to simply multiply these two. Okay? So this is the current, this is the period. So I can just multiply these two to calculate how much charge passes through one period. Okay? Now what does that give me? The total charge that passes through a given point over one period. That gives me the total charge in the ring, right? So imagine that there are some protons here, it's moving here. Of course, there are also some protons moving over here, moving over here, moving over here. They're just moving. So as this proton goes around and comes back to the same point, all the charges in the ring are going to come around and pass through this point. And how much does this take? It takes one period. Okay? So the charge that passes through this point over the time of the period of revolution for a given proton is going to be the total charge in the ring. As one proton goes around and comes back, all the charges in the ring actually has to pass through this point and produce this current. So the charge in the ring is going to be the current in the ring times the period. Okay? And you can multiply these two, so 11 times 2.1 is going to be 23.1 times, this is 10 to minus 14 coulombs. Okay? So this is the total charge in the ring. Now to calculate the number of protons in the ring, you have to divide this out by the charge of one proton. Okay? So this is like perhaps similar to you're getting a bunch of eggs from the supermarket and you're paying like the total sum, let's say 100 liras, and you're saying that one egg actually costs one. How many eggs did you actually receive? Right? So you divide the total amount of money you paid divided by the amount of money one egg costs, and you get the total number of eggs. So this is the total charge you have. If you divide by the charge of a single proton, then you get the total number of protons. So the number of protons is going to be the Q in the ring divided by Q of proton, and this is going to be, so 23.1 times 10 to minus 14. This is, I think, 1.6 times 10 to minus 19 coulombs, something like that. So this is going to be a large number. Okay, it's not on the order of Avogadro's number, but it's still going to be a large number. Something. So this is like 10. That is 5. So something like a million. Something of the order of a million protons that are going around at a given time in the Tevatron accelerator in Fermilab. Okay? So there are a lot of ways to go about this. So this is, I think, algebraically the simplest way. But if you do this another way, that's also fine. As I said, you can also calculate the frequency from this, and then from frequency you can go to you can calculate the total charge that passes through, and so on and so forth. But I think if you could follow this reasoning, this will be the most straightforward one.